Good afternoon, students. Today we are going to discuss about a new topic, which is nothing but liquid level control system. So in the last class, we studied about maintaining the temperature of liquid available in the tank. But this class, we are going to use we are going to study about the liquid level control in the system, or liquid level control in a particular tank. So for that, I'm using the following setup. So this is my tank. I'm assuming that this is a tank, and the head of the liquid within this tank is the H. I'm using the parameter H to indicate the head of the liquid within this particular tank, and I'm assuming that there is a measurement system. So this measurement system is measuring the present head of the liquid within the tank, and that value is taken by the control system, controlling block, as an actual level. And this actual level, that is a measured head of the liquid within the tank, is compared with the reference level, at what point you would like to maintain the head of the liquid within the tank. So that is taken as a reference level, means the present height of the liquid within the tank is always compared with the reference level. Based on the result of this comparison, the controller is going to takes the responsibility to turn on and turn off the supplying the liquid into the tank. So here I'm assuming that Q0 is means I would like to take the liquid from the tank from this particular area, and I'm supplying that liquid into the tank from this particular area. Okay, so I'm assuming that the volume of the liquid flowing per second out from the tank is a Q0, and volume of the liquid which is supplying into the tank is a Qi. Volume of the liquid flowing per second into the tank is a Qi. So as I said, the controller is always comparing the actual value with the reference value. Whenever there is a difference, then the necessary step is going to be taken care by the controller. Means if the reference level is greater than the actual level, then the controller takes the responsibility to turn on the pump so that the liquid is going to be supplied into the tank. If at all the actual value is moving a little bit greater than the reference value, then immediately the controller is going to be takes the responsibility to turn off the pump, so that the liquid which is flowing into the tank is going to be stopped. So this is what the basic system in order to maintain the liquid level in a particular tank. So these kind of systems are going to be used in the industrial area. So here, as I said, H is nothing but it is showing the head of the liquid. So here I missed out one parameter which we are supposed to take. It is there in your the PDF which I sent you. So here we you are supposed to take it as a E, means the present head of the liquid sensed by the measurement system. Now I'm assuming that variable is a E. And one more assumption is it is not the assumption. One more thing you are supposed to focus on this area is whenever there is a change in the liquid height, then immediately the Qi is going to be changes. Means if the liquid height that is the actual height is equals to the reference level, then the Qi is supposed to be 0. If the liquid height is less than the reference level, then the Qi is going to be supplied into the tank. If the liquid height is greater than the actual level, then obviously Qi is going to be again 0. So this is what we are having in the in maintaining the liquid level in the tank. So this is a setup. So I think you all got this setup. So let me go another case when you are trying to represent this system in terms of the control system. So here we are assuming that it is a controller block. Now this particular controller block is having certain gain. I'm assuming that as that certain gain is a K. Okay, so this is the Qi. Qi is nothing but the what is that volume of the liquid flowing per second into the tank. Q0 is nothing but volume of the liquid which is flowing out of the tank per second. So this is what the Q0. So this is the pump to supply the liquid into the tank. Okay, so this is all about the setup which we are going to use in order to maintain the liquid level in a particular tank. Now, in order to represent this entire system in terms of the control system, we are supposed to consider means we are supposed to draw this particular one in terms of the means if you want to represent this entire setup in the control system, what you are supposed to do means you are supposed to do some mathematical analysis based on this particular setup. Okay, so if you take this particular one, SEMA, we are taking the liquid out from the tank with a volume of Q0. So when you are dealing with the liquid flow through the tube, if you want to analyze the volume of the liquid which is flowing through the tube, we are supposed to take one equation called as a Poiseuille's equation. All of you know that one, right? The Poiseuille equation main intention means the Poiseuille equation is there in order to analyze the liquid flow through the tube. So here we are assuming that the liquid which is flowing through the tube is following the laminar flow, not the turbulent flow. Okay, which is following the laminar flow, not the turbulent flow. So let us see the Poiseuille's equation. All of you know that one, but let me show you that. Okay, so this is what my Poiseuille's equation. So here, as you know that the volume of the liquid flowing, there is a volume of the liquid which is flowing through the tube per second can be calculated using the equation. So here I am assuming that Q naught, which is the outflowing liquid volume. So Q naught is equal to the pi by 8 into P into 8 to the power of 4 by neta L. So here the P is nothing but the pressure experienced by the liquid when it is passing through the tube. Okay, now flowing through the tube. And A is nothing but the what is that radius of the tube. Whatever the tube you are using, its radius. A is indicating the radius of that particular tube. Neta is nothing but the viscosity of the liquid, and L is nothing but the length of the tube. So here I am rewriting the same equation in terms of the pressure change within the tube. So which is nothing but P is equals to the 8 neta L by pi into 8 to the power of 4 into Q naught. So the same equation, what I am doing is, so which is there in your material, I am going to your material which I sent you through the WhatsApp. So here we are having the change in the pressure now. So that change in the pressure is indicated using this equation which we have seen. So means there is a change in the pressure when there is a change in the pressure when the liquid is passing through the tube. Means at the center of the tube we are having certain pressure. At the near the walls of the tube, the pressure is going to be changes. So I am assuming that change is nothing but this term. So here I am rewriting the same equation in terms of the fluid resistance which we know. So here I am assuming that R dash is nothing but the fluid resistance which is equals to the what 8 neta L by pi into 8 to the power of 4. So I am reducing this factor. This factor is nothing but the what is that fluid resistance. So I am rewriting this equation in terms of the fluid resistance, which is the change in the pressure is equals to the fluid resistance into the volume of the liquid flowing per second. So this is the change in the pressure, pressure when the liquid is passing through the tube. So this is the equation number 2. I am assuming it as the equation number 2. And another case is, we know that when we are taking the liquid, if you are placing the one element inside that particular liquid, means if you are placing the element, or if you are considering the liquid height, let us suppose I am having the certain height. So the pressure, there is a change in the pressure when the liquid, when you are considering the liquid at different points within the container. So if I am assuming this is my container, so I am assuming that, I think all of you are able to see this one, right? So I am assuming that this is a liquid. So as all of you know that the pressure experienced by any element which is placed within the liquid is going to be uniform at equal height, and the pressure experienced by the element at another height is going to be changed. So here I am taking the pressure change in the liquid at two different levels. Pressure change in the at two different levels. To calculate the pressure change in the liquid, we are having one equation called as a gauge pressure. We are having one equation called as a gauge pressure, which you know that one. So from that particular gauge pressure equation, I am writing the change in the pressure is equals to the H into rho into Z, where H is nothing but the head of the tank, head of the liquid, head of the liquid which is there within the tank. Rho is nothing but the density of the liquid. Z is nothing but the acceleration due to the gravity. So that is nothing but the Z. Okay. So now we are having the two equations for the change in the pressure. I am equating these two equations. So when I am going to equate these two equations, I am going to get some mathematical expressions. Wait a minute. I'm going to get some mathematical expressions. All of you have these notes with you. So H rho Z is equals to the R dash Q naught. And if I'm rewriting this equation in terms of the head of the liquid within the tank, then H is equals to the R dash by rho Z into Q naught. Rewrite that one. So I'm introducing one new term in order to avoid the complexity of the equation. R equals to the R dash by R rho G, which is the equation number 5. So I'm assuming the R is nothing but this much. So finally you got one equation, H equals to the R into Q naught. I'm assuming this one is equation number 4. And another case is when you want to know the change in the means rate of change of the liquid height, rate of change of the liquid height within the tank, rate of change of the liquid height within the tank. If you want to know that one, what you are supposed to do initially, what is the means how much change is there in the height of the liquid within the tank. If you want to know that one, if you further, if you take the difference between the outflowing liquid, volume of the outflowing liquid and the volume of the inflowing liquid, if you are taking the difference between those two parameters, then you are going to get the rate of change of height of the liquid within the tank. So that can be written in terms of the equation, which is nothing but here C is nothing but the capacity of the tank. Here the C is nothing but the capacity of the tank, which is multiplied with the change in the head of the liquid or head of the liquid with respect to the tank is equals to the difference between the volume of the liquid inflowing liquid as well as the outflowing liquid volume. The difference between the inflowing liquid and the outflowing liquid volume. Now we know that Q naught is nothing but what from the equation number 4? Q naught is equals to the H by R. So if you are substituting this value in equation number 6 right over here, then you are getting the new equation, which is nothing but the RC into dH by dt plus H equals to the RQI QI. I'm assuming that is the equation number 7. And another case is that QI is equals to the KE na. So in the means during the initial explanation of this topic, what we said is I told you that we missed out one parameter in representing this diagram, which is nothing but the E. So the actual height purely depends on the present supply. Means if the actual height is equal to the reference level, then the what is that error between these two is going to be 0. So obviously QI is equal to this 0. So if there is a difference, then how much amount of difference is there for up to that time? Means up to that difference, the QI is going to be supplied by the pump, which is going to be turn on turn off by the controller. So there is a relation between the actual height and the inflowing liquid. So I am giving that relation in terms of QI is directly proportional to the E. So here you are supposed to represent the E, but I am missing out that one in the diagram. You just take down, but it is there in the given material. Okay. So here the QI is look at this. QI is directly proportional to the E. If you remove the proportional constant because of the what is that? That is a proportional constant. The proportional constant. Then you are going to get the QI is equal to K into E. So I am assuming this number is the equation number 8. Now we have the two equations. Based on these two equations, we can draw the control system for our liquid level control. For our setup, whatever the setup which we have seen initially, that is for this diagram. So for this diagram, we can draw the equivalent control system based on the equations 8 and 9. Based on the equations 8 and 9. Yeah. Based on the equations, where are they? Based on the equations, based on the equations 7 and 8. But if you want to represent that entire setup in terms of the control system, these two expressions should be represented in the frequency domain. These two expressions should be represented in the frequency domain. For that, I am applying the Laplace transformation to the equation number 7 as well as to the number 8. So after applying the Laplace transformation, as all of you know that one, if you are applying the Laplace transformation to this particular equation, then you are going to get the if you see this one, it is a there is a change. So it is a variable is the h now. So it is keep on changing with respect to the time. So it is a first order system. When you are having the Laplace transformation of first order system, which is nothing but L of Laplace transformation of f dash of t is equals to the s into f of s minus f dash of 0. Okay, now so this is the equivalent this is the Laplace transformation equation for the first order system. So here I am assuming that in my case I am assuming that the initial conditions are equals to the 0. Initial conditions are equals to the 0. So as I am applying the Laplace transformation to the first order system, then it is going to be the s into h of s based on this s into f of s. So it is going to be the s into h of s. So RC is always constant. It is already constant. So plus h of s equals to the RQI of s. And after that, I am rewriting this equation like this. Okay, now I am rewriting this equation like this. and after doing the simple mathematical calculations, I'm getting this equation. I'm assuming that the tau is equals to the product of R and C. So after that, from the equation number 8, we have the equation number 10. Okay now, so if you apply the Laplace transformation to the equation number 8, you are going to get the Qi of S is equals to the K into E of S. From the now, from the equation number 9 and 10, we can draw the, what is that, control system diagram, which is a closed loop system diagram for the liquid level control setup, which we have seen initially, that diagram. So which diagram? To this diagram, we are going to draw the equivalent control system block diagram. Wait, one second. Look at this. So from equation number 9, from equation number 9, if you see this one, Q is becoming the, what is that? Q is becoming the input to this system, and H of S is becoming the output to this particular system. If you see this one, from the equation number 9 and 10, this is the equivalent closed loop system, that is a control system block diagram for the given liquid level control system. So here, what we are having is this block is representing the controller block. What is the use of the controller block in the setup diagram? It is always measuring the present head of the liquid within the tank and comparing that one with the reference level. Whenever there is a change, then that change is going to be indicated as an error signal. So this error signal is given as an input to the what is that, first order system, which is not, but it is not the first order system. The error signal is given as an input to the controller block, whose gain is a K. So after that, this one is given as an input to the what is that, process element. Process element is nothing but which is equals to the 1 by tau s plus 1. So this one is given as an input to this particular process element, and the output of the process element is taken as a present height of the liquid within the tank. So if you see this one, 1 by tau s plus 1 is nothing but it is indicating the first order system. It is indicating the first order system. So based on the equation number 9 and equation number 10, this is the equivalent closed loop, control system for our setup, which we have seen in the initial stage of this particular class. Okay. So now, what we are supposed to do after getting this one, we are supposed to apply the we are supposed to calculate the steady state error response. So we are interested to calculate the steady state error for this particular system. So as you know that in order to calculate the steady state error to a particular control system, you are supposed to apply the final value theorem. So in this case, the error signal is nothing but the E of S, and input signal is nothing but the reference signal, which is the R of S. Now, what I am going to do is, I am going to take the E of S as an output signal and R of S as an input signal. When you are taking the output from here and the input to here, as we have seen introducing the analysis at the input as well as the output level, we have redrawn the circuit diagram, right? We have redrawn the circuit diagram. So based on that particular redraw, so the same diagram, this diagram, if you are taking the E of S as an output, then I am going to get the signal like this. So it is a R of S plus minus, and you are going to get one block, K into G of S. I am not indicating the complete term. I am assuming that this is one block and it is another block. When the two blocks are concatenated in the closed loop system, the total block, the two blocks are reduced into one block by multiplying their individual gains. So I am multiplying these individual gains, K into G of S, and I am taking the E of S right over here. I am taking the E of S right over here. Okay, so this is what we are having now. So to this particular one means output is the E of S, input is the R of S. I would like to write the equation, that is the relation between the E of S and R of S, so which is there in the material. So as we don't have the board, it is very difficult to me to represent everything following the material. Without following the material, we can easily have the analysis. Okay, let it be. It is a what is that? As we don't have the board, it is very difficult. So here we are having the E of S, a ratio between, I am taking the E of S as an output now, obviously the R of S is an input. The ratio between the E of S and R of S is nothing but it is going to be the 1 by 1 plus K into G of S from this particular diagram. So this is a forward path gain, it is a 1, and it is a feedback path gain. which is a k into g of s. From the transfer function, output by input is equals to the forward path gain by 1 plus forward path gain 1 into k into g of s, feedback path gain. Now I am substituting. This is the equation. Okay, now from the first what is that? First topic of our third unit, which is the transfer function. So here this is the equation, and I'm substituting the g value over here. So after substituting this one and after the simplifying this term, we are going to get the tau s plus 1 by tau s plus 1 plus k. Now here I'm rewriting this equation in terms of the error signal by moving this r of s to the right side. Then I'm going to get the tau s plus 1 by tau s plus 1 plus k into r of s. So r of s is nothing but the reference level. Reference level is nothing but at what point, at what height you would like to maintain the temperature of the liquid. Okay, at what height you would like to maintain the temperature of the liquid. So it is a reference signal which is nothing but the input signal. Okay, so now to this equation I'm applying the final value theorem. So what is the intention of the final value theorem? To calculate the steady state error, we are applying the final value theorem. So we have seen what exactly the steady state error. I'm not going to repeat that one. So here, after applying the final value theorem to this equation, the steady state error is equals to the limit t tends to infinite, e of t is equals to the limit s tends to 0, s into e of s. So after this, I'm substituting the e of s value from the equation number 12, and I'm going to get this one, this equation. So I'm assuming that the reference signal is nothing but the unit step signal. I'm assuming that the reference signal is nothing but the unit step signal, which is the r of s. The unit step signal, which is the r of s. Okay. So r of s unit step signal in means the Laplace transformation of the unit step signal is nothing but the 1 by s. 1 by s. So total equation is limit ESS equals to the limit s tends to 0, s into 1 by s into tau s plus 1 by tau s plus 1 plus k. So after doing all the mathematical calculation, you will come across this term, ESS. You will come across the ESS, which is a steady state error. So this equation is showing that with how much factor the steady state error is going to be reduced because of the unit step signal. With how much factor the steady state error is going to be reduced because of the what is that unit step signal. Means the steady state error of a particular control system purely depends on the steady state error of a particular control system purely depends on the input signal which we are taking as well as the order of the system. So order of the system we have seen, first order system, second order system, all those things. Okay now, so order of the system is nothing but the number of what is that poles which are there in the denominator of your transfer function. So here we are taking the first order system. From this based on that one, so here the conclusion point for the steady state error is the steady state error value is going to be reduced by a factor of 1 by 1 plus k when there is a step change in the input signal. When there is a unit step change in the input signal, then the steady state error of this particular control system, steady state error of this particular control system is going to be reduced by a factor of 1 by 1 plus k. Okay, so this is all about the steady state error and all those things. I hope all of you realize the concept. So if you are having any queries, then what you do is you just post in the WhatsApp group. So here there are lots of problems while recording the videos because of shutdown. Means I don't have the required amount of equipments. If you are facing any problem in viewing this, in watching this particular video classes, so let me know that one also, because my intention is I don't want confuse you people. So because of that I'm using the projector type scenario. Okay, no, projector type scenario, and I don't have the required amount of equipment, that is a software editors, all those things, because right now I'm in the village, so I don't have the editing software also, because lack of the broadband connections in the village, and also the lighting effect is also affecting the video classes. If you are having any difficulties while watching this particular videos, means the video classes, then let me know, so that instead of recording the videos like this, I'll go with the recording the what we say, the desktops, means screen recording format. So I thought that if I'm going for explaining the classes using the screen recorder, then you may feel the difficulty in realizing the concept which I'm explaining. There in that recording session, I'm going to give the voice over only. So only the video is going to be comes, but I'm not going to appear. So it is not a matter of appearance of my photograph, but only the thing is, I think it is not good for the students to give the voiceover on a video. To give the voiceover on a video. So otherwise, I'll do one more video on this particular voiceover. So I'll put the both videos if possible. Then you decide which one is better for you to realize the concept. So this is all about the liquid level control system and the factors which are affecting because of the lockdown. So I think all of you enjoyed the video. Thank you.